welcome back to Decaf-Math. I hope that you're doing very well. So today, let's talk about related rates. This topic was requested by a viewer on this channel, so hello, and I hope that you find this helpful. Related rates are a type of problem that involve derivatives. So this is often introduced in calculus. And so I just thought I could introduce these types of problems with one example and also just kind of talk about them in general. And then if you want, we can definitely work through more practice problems. But since it was a general request, I thought, hey, I'll just start generally in case, work as though we know nothing. Let's see. So here's my little Hello Kitty. A subscriber and a friend on this channel sent me these adorable Hello Kitty stickers. And when they sent them, they were like, why on earth do you need Hello Kitty stickers? And I was like, duh, just stick on everything. Because I love cute stationery and stickers and pens and stuff, so there you go. She's hanging out with us today. So yeah, I did start kind of writing a problem. I didn't copy it from anywhere, but the thing is, I call this like the ladder problem, and the thing is, there are only so many types of related rates problems out there. I feel like because you need to use some sort of base formula. So I definitely borrowed a common one. I call it the ladder problem because the general idea is always the same, even though, questions might have subtle changes there. But I wanted to start with this type of problem and we'll take it from there. So first of all, related rates. The idea here, and I didn't know this for the longest time because I guess it's so, quote, obvious, but related rates, the reason that these problems are called related rates problems is because we are, relating rates of two variables or multiple variables, really, not just two. But the key setup is that, you have a formula based on your word problem, okay? It might be a volume formula, like this is the volume of a sphere that relates the radius with the volume. This is my Pythagorean theorem, right? You might have surface area or just area or whatever, just based on your problem. But the idea is that you have at least two, you have multiple variables that are related by a specific equation, okay? But the reason we are now going to relate rates is that each of those variables, or a few of those variables, are themselves functions of time. So they are changing. For instance, the volume of sphere, the radius might be changing at a particular rate. So each of those variables are functions of time. So therefore, when we take the derivative with respect to time, we can do some calculations. Of course, we have to apply our normal calculus rules, like our derivative rules, but we can relate the rates of those variables. So rates are functions of time, usually, okay? Usually it's a variable that is not one of these two, okay? So or three, or however other many, it's usually with respect to some other variables, okay? So typically it is going to be time, especially in these word problems, but if you have a random other type of question that's not, then, adjust as needed. But the reason so let's just go right into the latter question. This is common enough that I even just call it that. For the students that I've tutored over the years, it's common enough that they've come to me with the same type of question that involves some sort of ladder leaning against some kind of building. So that's where I get this concept. I made up these numbers, but kind of picked them so that they would be sort of convenient. So if this happens to match up with something you've seen before, then I promise I didn't copy this anywhere. However, the idea is pretty much like the same, even if there might be subtle differences in the way that the question's phrased, or they might be asking slightly different things. But the concept of the ladder question is that you have a ladder that is leaning against like the side of a building, okay? And I kind of already drew it here. And so you, in this case, let's see, a 17-foot ladder is leaning against a building, okay? I'm not a wordsmith, I'm just Decaf-Math here, so my writing might be terrible, but this ladder in my problem is 17 feet long, okay? And in fact, I even can generalize most of the questions that I've seen have a ladder that's somewhere between 12 and 20 feet. And 17 is a nice number because you can work with the square and all that stuff, so there you go, anywhere from there. But the idea is the ladder is leaning against the side of a building, and the bottom of that ladder is sliding outwards this way, okay? So either someone is pulling it, or it's just slipping, or, you know, whatever your word problem says. In this case, the base of the ladder is sliding at 1.5 feet per second, okay? So this is sliding at a rate of 1.5 feet per second. So notice the units. The units tell you it's some sort of velocity, right? Or feet per second, right? Like miles per hour, right? Or meters per second, or whatever, right? So it's something per time, it's distance per time. So that means that this base is going to be sliding there. So that is a rate. But then the question is, how fast is the top of the ladder sliding down the building when the base of the ladder is 8 feet from the building? So the question is, how fast is the top of the ladder sliding down the building? Okay, at a particular time, but we'll see that here in a second. But how fast is the top of the ladder sliding? So as you would expect, if you think about this, the ladder is not going to bend or fold anywhere, at least hopefully. But in this question, this is just going to be sliding, which forces the top of the ladder to slide down, right? Because the distance has to be the same. So it'll just be like sliding. So it might go from here to like here. Oh gosh, that's awful. I'm sorry. Okay, so it might go something like, yikes. Okay, something like that. Okay, so you'll see that as this thing slides, as the base gets pulled out that way, the top is going to start falling down, right? Like that, naturally. So it's going to go down. So it's saying at the particular instant, how fast is the top of the ladder sliding down when the base of the ladder is 8 feet from the building. So we don't know how far it starts, okay? We don't actually know how far the base of the ladder starts away from the building. All we know is that the ladder is 17 feet long. But we do know that this is being pulled out at 1.5 feet per second, and we're asking what happens when at the exact moment that the base is 8 feet. So the question is when it's 8 feet. 8 feet, at exactly 8 feet. And so the question is at a particular moment, which is expected because we need some way to sort of visualize or calculate the rate at a particular moment, because at any other moment, the next moment, it's going to change, or it could change potentially depending on equation, okay? But that's it. So you'll see that we're looking for this rate, and we know this rate, okay? And so of course the ladder stays 17 feet, it doesn't grow or anything, which is what forces this thing to slide down when this slides out, is because the fact that this length is always 17, okay? So that's the general idea. Now the thing is, with these types of questions, you want to use some formula. Like I said before, you want to visualize what's happening and use a formula to relate the things that you're trying to find. So in this case, what I am seeing is that this horizontal distance is changing. It's changing this way because it's sliding that way. So the distance from the base of the ladder to the wall is changing, and I'm going to call that distance X. Okay, let's see here if I can label this nicely. So I'm going to call this X. Okay, and X is a variable, right? So X could be here, it could be here, here. It's just a general variable. And I'm going to call this vertical distance Y. Okay, so the vertical distance is always just from the top of the ladder, to the bottom. Okay, that distance. And the X is always going to be the distance from the base of the ladder to the wall, horizontally. Okay, so notice that X and Y are constantly changing, so we are talking about instantaneous rates. Okay, but whatever X and Y are, whatever they are functions of time, because it's changing at this rate, X is changing at this rate, and I'm looking for what rate Y is changing. How fast is it sliding down? The real question is we're trying to find dy dt. When, and then at a particular point, when, and then this particular question says when the base of the ladder is 8 feet. If the base of the ladder is at 8 feet, that means when X equals 8. So that's the question. You see that? I hope that makes sense. So you have to set up your situation based on what they're asking, but usually it will imply like at a particular time or at a particular distance or at a particular situation, okay? So what we do for this type of question, again, start with some kind of formula that relates your variables that you're trying to find. In this case, we know we're solving for dy dt, which is the rate which is sliding. We know dx dt is 1.5 feet per second. And here's a little test. Why is this rate positive? Why did I write 1.5 and not like negative 1.5? The reason is because dx dt is the change in x, the change in the distance, and over time, and that distance is growing, it's increasing, which means that the derivative is positive. Okay, and we know that because the base is sliding that way, so this distance is increasing. Okay, so our question is then, what is dy dt, which we just said. And so the thing is, we need to relate x and y in the first place so that we can take the derivative with respect to time. So I don't know anything about x and y in general, okay, except that they are related by the Pythagorean theorem. I know that x squared plus y squared equals 17 squared. Always. So no matter what instant I have, whether at 8 feet or any other time, right, or distance, I just know that x squared plus y squared equals 17 squared. And this is why the ladder problem is so common, because how else would you have a situation where something is like the hypotenuse of a right triangle? And I mean, there are some, there's like the lamppost questions or shadows and stuff like that, and we can work through some of those as well, but I don't know, maybe you can get creative and come up with your own. But this is the formula that we're going to use to relate x and y. Okay, so now what we're going to do is take the derivative with respect to t on both sides. So this is where it can get kind of tricky. So I'm just going to, this is from Pythagorean, okay? Pythagorean, because you see the right triangle here. And the fact, I guess I didn't really simplify 17 squared, but that's okay. We don't need to. I'll just rewrite it just to be clear. We don't need to because the point is that it's a constant. So what I'm going to do is take the derivative on both sides with respect to t. And this is what makes it a rate. So parentheses like this, parentheses like this, okay? So now this is where it gets kind of complicated. So remember, x and y are functions of t. Just the way that the question is phrased, and just knowing it's a related rates type question, it is safe to assume that, okay? Because the x distance is changing with respect to time, and not only that, we know dx dt is 1.5, it's given. So that means that if x is a function of time, when we take the derivative here, remember that you can distribute, so to speak, the derivative over like the addition. It's not exactly distribution, but you take the derivative of the first thing plus the derivative of the second thing, and that is allowed. Okay, so let's start with that. And then let's see here. Okay, of y squared. And then I guess we might as well take care of this on this side. What is the derivative of 289? That's a constant, right? So that will be 0. Okay, it doesn't matter that we're taking with respect to t. The derivative of any constant with respect to any other variable is 0. Okay. So that's nice. The side's nice. So now we need to think about the fact that x and y are functions of time, which means that we need to actually apply the chain rule. This might be the trickiest part, I think, in my opinion. We did implicit differentiation, if you want to check out that video, but really all you need is the chain rule. You just need to keep in mind that x is a function of time. So what I would do is you have to take the derivative of x squared in this part with respect to x first, which is just 2x, and then you multiply by the derivative of the function of time part. So it's 2x dx dt. So I'm gonna just kind of go over this part, just kind of linger on this a little bit, because this part gets really confusing, I think. So you know when you normally have like you're trying to take the derivative of ln of t squared, okay? So if you take the derivative of this, you need to use the chain rule with respect to t. You take the derivative, if x is a function of t, for instance, like this, to find dx dt. You take the derivative of the outside function, so you take your normal derivative, which would be the natural log, so like 1 over t squared, 1 over t squared, because the natural log, like the derivative of ln of x with respect to x, is 1 over x, okay? And while keeping your thing on the inside, so 1 over t squared, but then you also need to multiply by the derivative of the thing on the inside. was trying to just kind of refresh us here on the chain rule. But the idea is we can take the normal derivative, that x is a function of t, but it's just 2x. Okay, so the derivative of x squared with respect to x is 2x, but x itself is a function of t, so we need to multiply by the derivative of x, dx dt of the inside part. Okay, so same thing with the y. So the derivative of y squared with respect to y is 2y, but since we're trying to find the derivative with respect to t, we are also going to multiply that by dy dt. Okay, and then we get equals 0. So the only reason we're doing this thing is because we know that x and y are functions of t. Like x and y themselves are functions of t. We don't know exactly how to write out that function. We just know that it's changing with respect to time as well. I hope that makes sense, but let me know if you want to come back to this some more, okay? Either way, it's going to be crucial that you understand how to use the chain rule for these types of questions, because everything else is about filling in the information that we know, okay? So now the question is, we're still looking for dy dt, which we are a step closer to doing. We have this is what we're trying to solve for, and now we know dx dt is 1.5, so we're just going to plug that in. 1.5. We know that the question is asking for the instant when the base of the ladder is 8 feet away, which means x would be 8. Okay, so 8. And now, what other variable do we need? We need y, but we can get y by solving, because the 8 feet gives us an idea of what dy dt we're looking for, right? It's at a particular instant. So at the instant that x is 8, we can actually solve for y, because we know that 8 squared plus y squared must still equal 289, which is 17 squared, right? No matter what our x and y is, they must satisfy the Pythagorean theorem. So we can just solve for this. 64 plus y squared equals 289, which means y squared equals 289 minus 64, which is 225. And that's actually why I picked 17. That's why I picked these numbers, but I wouldn't be surprised if someone else thought to use like whole numbers like this. Okay, convenient Pythagorean triples, so that's why I said. So that means y must equal the square root of 225, which is 15, and it must be positive because y is the distance, the height, so there's no such thing as negative 15 feet for this type of question. Okay, so y equals 15 when x equals 8. So that means we have y. So we're looking for dy dt. So it doesn't really even mean much that we found that this is 15. But now we have all of our variables covered except dy dt, which we can solve algebraically. So we have, let's see if you can still see this. I hope so. I'm sorry if it's kind of hard to see. Let me know if you want me to like zoom back in on this. But maybe I can leave a link to the picture. But we have 2 times 8 times 1.5 plus 2 times 15 times dy dt equals 0. So notice that we only have one variable now, and it's just this. So that means dy dt equals negative, because I'm going to move 2 times 8 times 1.5 over here, subtracted. So I'm just going to do this in my head if I can. 2 times 1.5 is 3, times 8 is 24. So negative 24 over, and then I'm going to divide by the 2 times 15, which is 30, like that. So that's just going to be negative, if I simplify that, 4 over 5. Is that right? I think that's right. Okay. So, hopefully you're pretty comfortable with the algebra algebra here, but you can write one more step to multiply this out, but just in the interest of space, I wanted to go ahead and do that. So notice that we just calculated dy dt is negative 4 over 5, which is, I'm just going to put negative 0.8 just to match the 1.5 feet per second. So our answer is, the question is, how fast is the top of the ladder sliding? I would say it is 0.8 feet per second would be my final answer. And then just to be super clear, I would write down. And so that's why our answer was negative 0.8, is because that implies, just like this 1.5 is positive, the negative 0.8 implies that the distance, the y, remember the y is the distance from the top of the ladder to the base. If that is negative, that means that that is shrinking, it's decreasing, which is what we're expecting because the ladder is sliding down as this goes out. So if the question is how fast is the top of the ladder sliding down, it's kind of redundant to say down, but the answer is just 0.8 feet per second, or 0.8, whatever you prefer. Okay. I hope that this was interesting. If you want me to kind of rework it out slower, or draw it out more, or if you want me to like type up the question so that we can go through it again, I'm actually happy to. I just wanted to get this video out in case anyone's actually trying to work through practice problems for finals or anything like that. But this is definitely a common type of problem, so if you have questions, be very, very clear about what your x and y mean, and what type of equation you are trying to set up, and be clear with what it means to change with respect to time. And remember that when you take the derivative here, once you set up which equation, when you decide what equation you are using to relate your variables, then the issue is to take the derivatives with respect to time so that you can relate the rates. And when you do that, remember to use the chain rule. It will usually involve the chain rule, like it's usually with respect to time. Sometimes volume questions or surface area questions will involve change with respect to the radius or something like that. So, don't get too attached to that idea, but just commonly it's with respect to time. But either way, as long as you keep in mind which variables are actually functions of whatever else, when you take that derivative, don't forget the chain rule. And the chain rule just means take the derivative as you would normally according to the variable that you would think to, like the derivative of x squared is with respect to x is 2x, then multiply by the derivative of that variable x that's actually a function of another variable, so dx dt or dy dt. Okay, I hope that helps. I will post another video soon with just jumping right into a practice problem, but I wanted to just kind of get this set up today. Anyways, let me know if you want to see any other like specific problems. That's always the most helpful. If you're stuck on anything, let me know. I'm trying to prioritize the requests that sound like, maybe I could be wrong, but just sound like you're like anyone who's actually studying it right now in school or studying it on their own. And of course there are some really cool, interesting topics in general that I might cover over this summer or something like that. I'm not really sure, but this is exam time for a lot of people, so that's kind of what I'm trying to go for, is cover these big picture topics. So yeah, anyways, I hope that this was relaxing regardless of whether or not you know this stuff, or if you have no idea what's going on. And if you are just drifting off to sleep, sweet